everyone. I've set up this esp32-cam for visual recognition of American Sign Language. The esp32-cam runs the standalone model without the need to be online. I'm using Tensorflow Lite, and this technique it can also be generalized to other Tensorflow computer vision models, not just the American Sign Language. In the rest of the video, I'll show you exactly how I made this. And what we're looking at there now, I'll just point out, so that's a W, a hand signal for a W, and that's the most likely letter is W, and the second most likely letter, the letter with the second highest confidence, is an F. A, B, C, the training data I'm going to use comes from this sign language MNIST set, which is on Kaggle. And I'm just going to download this. And with this, if we scroll right down, someone's already made a notebook where they say they get 100% accuracy. So I'm going to download that as well. And I'm going to try and reduce the size of the model that's used in this notebook, so that it fits on the ESP32. I've downloaded the notebook from Kaggle that builds a neural network for the American Sign Language inference. So it takes in these 28 by 28 images and it spits out what letter it is. It does some inference on them. So, and I've made some changes to the notebook, and I'll go through these with you now. And the most important changes I've made are, one, I've reduced the size of the model, and the other thing I've done is at the end of the notebook I've added on some code to export the model to a tflite model, so we can use it on the ESP32 microprocessor. Now, this is fairly non-trivial, so I'll go through it with you now. So this here is just, the notebook just starts out by importing our libraries, as do all notebooks. And we're using Keras for the model. And then we read our data, and you might need to change this, just this directory, just to wherever you save your data. And this data is available on the Kaggle website, which I'll link in the description. And then we massage our data a little bit. So we inspect our data. So these are all our letters, and this shows how many letters. So 0 is A, and 24 is Y. Z and J are not included. So 8 is I, and then J is 9, but that's not included. And then 25 would be Z, which isn't included because the numbering starts at 0. So all the ones that are included are shown here. A, B, C, D, and then J is missing, and Z isn't there. So so that's our American Sign Language data set, and then we put it in a form where, so at the moment it's the grey level images from 0 to 255, and we put it in a form. So in their notebook they normalize everything between 0 and 1, but I normalize everything between -1 and 1. So that's what all this code does. And then I've also added this part here for debugging, which basically I do is I output just the first 10 entries to a CSV file, just so I can play with that a bit later on. But then this is the normalized code. So what they have is they just divide everything by 255, like this. I just divide by 127.5 and subtract 1. So I normalize everything between -1 and 1. And I do that because the example I'm following in the code is the person detection example. And that's how they, and basically the input in the C++ is as an integer, not an unsigned integer, an integer. So it's -128 to 127. So then when I quantize it, it's just better if I have it between -1 and 1. And that's all described. So their method of exporting it to tflite and with the person detection model is described in this website here. and I'll also reference that in the description. So then we have we examine some of the data. So this is from the notebook and data augmentation. So all this does is basically it shifts the data and does a few transforms on it. So we basically increase the number of training samples we've got, and then the notebook describes a convolutional neural network and the model. Here's the model. So this is my model here, and I'll show you their model. So what I've done is I've reduced the parameters here. So this model part here, so this was originally 75, this was originally 40, and this was originally 512. So I'll show you their model. So their model this is the original model that was used, which has 75, 50, and 512. And let's have a look how many parameters their model has. 264,000 parameters, and I wanted to reduce it to less than 100,000 parameters. So now let's see where most of these parameters are from here. 205,000 of these 264,000 are from the fully connected layer, which comes after the convolutional layers. So this has 512 nodes. And the reason there's so many parameters there is because in the fully connected layer, each one of these pixels has a weight for each node. So the number of parameters is the number of pixels plus 1 for a bias times the number of nodes. Whereas in the convolutional neural network, the convolutional filter, the number of weights is just the number of it's just the size of the filter. So this is a 3 plus a bias. So this is a 3 by 3 filter. So 3 times 3, that's 9, plus a bias is 10. So the number of weights on each of these input is going to be 10. So we've got 75. So therefore we've only got 750 parameters for this input layer. So I've reduced the size of the network, and I've got it down to 87,539 parameters. And the other thing I've done is I've taken out the batch normalization. Just didn't want to complicate things in the C++ code, and I didn't want to kind of introduce any bugs. So you can try it with batch normalization if you like. Then I run my model, I do my training, and my accuracy is 99.986%. So that's pretty good. And then the notebook also includes some analysis after model training, which you can go through. So this shows the accuracy. So the green is the accuracy of the training data, and the red is the accuracy of the testing data. So now if these two diverge, that means that your model is overfitting. But both of these are going closer to 1, which means that we don't have overfitting in our model. And then this is the part I've added. So this part here, and I'll put a couple of references in. This part here, we export the data, the model, the tflite model, the TensorFlow model, to a tflite model. So we have this representative data set function, and this basically tells the exporter, the converter, the tflite converter, how to quantize it, what range of values to quantize the floats into, because we're quantizing it as an 8-bit integer. So what I've done is 127.5 minus 1. So that's how it's converted. Basically, I'm just telling it how it's normalized, and then it knows how to quantize it. So then I convert my tflite model, and I get a few warnings, but I don't really know what they mean, and they didn't seem to have any impact. And then I write my tflite model, and the next thing I do is I have to export that tflite file to a .cc file. So I do that on the bash, on git bash. So I just open git bash, and this has this xxd command already on it. So you just have to basically go git bash and open that up, and then you just run that command, and that'll export it into a .c. And let's have a look at that file now. So it's in here. Here, this one. So, open with Notepad. And this is what it looks like here. So, it's basically, the whole model is now encoded in this hexadecimal file. It's just an array, basically, unsigned char array. And and basically you just paste this in to the example, the person detection example, and change a few other parameters, and it should work. And also at the end of the file, it just gives you the length of the array. Alright, so the next thing I do in this file is I reload the tflite model, and I just check that it's working. So it should give you 100% accuracy, or close to, if it's working. Then I implement it on the ESP32. So first I'll take you through the person detection example that came with the ESP32, which is the example that I'm working around, and then I'll show you how to go from there to implement your own model. So I'll see you in the next scene. Hey everyone, so I've wired up this TFT monitor screen onto this esp32-cam, and the first thing I'm going to do, I'm going to test the example that came with the Tensorflow lite library for the ESP32, which is a person detection, and then I'm going to try and plug my model into that example. Hey everyone, so the library I'm using for this project is the Tensorflow lite ESP32 library, and if we look through the examples, this came with a person detection example, which is the closest example I could find to what I'm doing. It's almost exactly the same. So it basically does inference from an image from a camera, which is what I want to do. And so I'm just following this example here to do my American Sign Language recognition. So I'll just load that up. The example sketch is loaded now, and it includes a number of files. So these ones here, the camera ESP files, are just for configuring the camera. And this one here, I guess, is the important one. This is the model. So this is basically the tflite model here, which is just a unsigned char array. And then the main file, I guess it just configures the camera, sets up the model, then captures the image, and then does the inference. But I've rewritten this, so I've taken out the main model, like it's like a car. So I've taken out the engine and I put it into a new body, and I've rewritten it kind of a bit more simply, so it outputs to a TFT using using this TFT_ESPI library, because the last file just output the last example, the example that comes with the library, outputs to a LCD, and it's all written in C, and it's a little bit more difficult to use, whereas this one's written in C++, so it's a bit easier to, it's just like one line of code to output the image to the TFT. Now a lot of this stuff is described in this article here, so I'll link this article in the description. So basically all the sketch does now is it configures the camera and the model. So first thing it does in the setup, basically initializes the TFT, and then just prints out a couple of a sentence to the TFT, just prints out this sentence here. Where is it? Here, starting up, just as a test that make sure the TFT is working. Then we initialize the model, which is from this array, from this unsigned char array, which is here. And we do some checking, allocate some memory here. Now, if we're using a larger memory, we have to use a pscalloc. We can't use the heaps caps malloc function. And then we check that the memory allocation was successful, and then do some op resolver stuff. If we don't want to do all this, if we don't know what ops we need, we can just uncomment this section here, and this will include all the ops, but it'll also add a lot more space. It'll add about an extra 100K to the program memory. And then we set up our model here, allocate tensors, and then in the loop, we capture our image. I just capture the first two images here, just to make sure I'm capturing like the most recent image that I'm clearing out the camera buffer. And then we downsample our image because I've configured the camera to capture a 320 by 240 image, which displays better on the TFT. And then I have to downsample to 96 by 96. And then once I've downsampled the image, I just followed what was in the example to convert it to RGB 565, and this converts it to grey level, to an integer grey level between -128 and 127, and then I write it to this image data, which is basically the input to the model. So the image data, where is it defined here? So it's just the same address as the model input, the integer 8 model input. And then we invoke the interpreter and we get our output, and we have basically two outputs. One is K person index and one is K not a person index. And then we just take the greatest one, and that's our inference, person score and no person score. So if person score is greater than no person score, we then write a green rectangle to the TFT, and if it's less, we write a red rectangle. So this means there's no person detected, and this means yes, there is a person detected. And then we delay for 2 seconds, and then we go back to the beginning of the loop. And I'll show you this working on the TFT in the next scene. I've got the tflite person detection model working, the one that came with the tflite esp32 library, and I've got that loaded onto the esp32-cam, and it shows the image on the TFT screen, and then there's a red square when there's no person and a green square when there is a person. So I'll tilt the camera towards myself and I'll show you what it looks like with a person. So there we go. That's no person, and now hopefully it's going to come up with me, which is a person, and then that's going to go green in the corner. Okay, so the way I've done this is I've mounted the ESP32-cam on top of the TFT screen, and then all the wiring's behind here. Now this wiring, and I've glued it all to some Lego, or attached it to some Lego. Now this wiring is a little bit difficult because I need to get the FTDI in there. Every time I change the code, I need to upload it, and there's a fair bit of debugging. And the other thing is, if I knock a wire out, it can be a little bit of a hassle because this TFT takes a lot of wires. And then, so what I've done is I've made up some PCBs. Well, I've ordered some PCBs from pcbway, who have very kindly agreed to pay for the PCBs for this video. And I've made the PCBs up on fritzing, and I'll show you how I've done that in the next scene. So fritzing allows you to do a 2-layer PCB quite easily, and I'm not doing anything that complicated. I'm just connecting the TFT to the ESP32-cam, and plus leaving room for an FTDI programmer. So I'll show you that in the next scene. This is my fritzing diagram, and I've just laid out all the components. So you just need something that's got the same, I guess, form factor as what you're using. So this is my TFT screen here, and I'm just using these pins here. And then this is my ESP32-cam, and I've got here some terminal screws and an FTDI programmer, and then just some spare holes. So you can design this, when you do the fritzing, you can design it in PCB mode, and then you can go and check that all your connections are, so design rules check. So that'll check it for you. And so there's two that are overlapping, and what it is here. So the orange, this is basically in 2 layers. So the yellow is 1 layer, the yellow wires, and the orange wires are another layer. So we can do 2-layer design. So if I move that to the top layer, and then I'll go and check again. and now it's ready to be output. All right, so now I can go here and I can output to like a Gerber file by choosing this one. And then once I've done that, I can just upload the Gerber files to pcbway. So on the pcbway website, I just go to quote now and then quick order PCB and add Gerber file, and then PCB, whatever my Gerber file is, I've got to put it into either a zip file or a .rar file, and upload that, and then just follow the steps, and it's really easy. Okay, so now I'll show you the actual PCBs. Okay, so my PCBs have arrived. So hopefully I'm going to replace all this wiring with whatever in this box. So let me open this up and get it out and we can see. Alright, so that's what they look like, and I'll pull one out. Oh wow, that's amazing. Alright, so it goes up like this, and then I can mount the TFT on here. That's for a bigger TFT, it's for a 2.8 inch, and I think this is like 2.2 or 2.4 inch. And I can put the esp32-cam like that. I just need to solder on some female header pins, and then the FTDI programmer goes in here like this. So now I've got it all like that. I can use this as like a camera with a TFT screen on it, and then I can avoid all the wiring, because all the wiring's here in like printed onto the PCB, printed circuit board. And then these are the terminal screws, which are for positive and negative voltage. So I'm going to solder on my female header pins and plug all this in, and hopefully we can get it working pretty soon. Goodbye, messy wiring. Hello, PCB. So I've soldered on the header pins now, so I can just plug the TFT and the ESP32 in. And then this here is for flashing it. So this connects the 0 pin to ground, and this is for the FTDI. And then on the back, I've soldered on the terminal screws, just because I'm going to mount the battery on the back of the PCB. So it's just going to make the terminal screws, it's just going to make it a lot easier to have the terminal screws on the back here. Here's one I prepared earlier. And I've mounted the esp32-cam here and the TFT here, as you can see. And the only wiring is coming from the power source. And I'm using a 18650 battery on a shield, which outputs a 5 volt. And you can basically use whatever power source you like, as long as it outputs 5 volts. So at the moment, I've got the person detection sketch running on this. So I'll just turn that on and I'll show you how that works. And if there's a red dot in the corner, that means that no person is detected. And now I'll point it at myself, and I'm a person. So now it should come up with a green dot in the corner. There we go. I'm going to show you how I updated the person detection model with the American Sign Language tflite model that I trained on Python. So if we recall where we were, we had this model that we output to a tflite model, the one that we got all the data from Kaggle for, and we got the notebook from Kaggle as well to train the model, and then we added all this stuff to output it to a tflite model, and the input type we made as integer 8 and the output type we made as integer 8 as well, and that's to line up with the person detection model. And then we converted the tflite, the model, to tflite, the Tensorflow model. So we had a Tensorflow model in Keras that we converted to tflite. Okay, and then this is the important part. We ran this xxd command in bash. I ran it in git bash to output the tflite file. So we wrote the tflite file here to output the tflite file to a .cc file. and I'll show you what that looks like. So that's this file here, and that's basically our model. So then we have to copy our array to our pdet-models.cpp file. So this is the file the model file that came with the person detection example. And the other thing, so we copy that array in, and that's fairly long. And then the other thing we have to do is copy the length of the array down at the end, and that length of array is given in the .cc file that's output from the xxd command. Alright, and the other thing we need to change is in our model settings file, the number of columns 28 and number of rows 28, because we're using a 28 by 28 image, and the person detection model uses a 96 by 96 image. And of course the categories, 24 categories, one for each letter except for J and Z, which wasn't included in the training set. And then I'll show you the changes in the main file. So okay, so this is an array of category labels, because the model outputs integers 1 to 24, and then I use this array to map the integer to a letter that's inferred by the network, by the model. And the other thing I've got here, this testimage.h. So this testimage.h file is like a raw image. It's just the grey levels of an image from the Kaggle test dataset. So I can input this into the model without the camera, without capturing it from the camera, just to test that the model's working on the microprocessor. So if I go here, let's scroll down a bit. Down here, and I uncomment this line here, then I have to comment this line. Then I'm going to import the test image rather than capturing the image from the camera, because this is the image here that's captured from the camera. And that way, if there's an error, then I know that there's something wrong with the model rather than something else going on. So this way I can isolate and make sure that my model is actually working. Alright, so the next thing I wanted to show you is the example. They allocate 81K for the model size, for the arena size, and I found 81K worked quite well. But if you're using a bigger model and you need more than 81K, you'll get an error message saying, say I need 160K but I only have 81K. So the error message is quite helpful on this. And then the other thing is, when you allocate the space using the heapsCapMalloc function, if you've got more than 81K, I'm not sure how much more, you're going to have to use instead pscalloc. If there's too much memory, if kTensorArena is too large, then you're going to have to use the pscalloc to use psram. So something like that. So that'll run probably a little bit slower because it's on psram, but if you're using a larger model, that's what you'll have to do. And I'd be interested to see how big a model you can actually run on this. So I might do that for another video. Let me just delete that because I don't want to mess up my code. And then everything just goes, okay, so there's this as well, which is the micro op resolver. And I've had to add a few operations to this, but that was all. I found out which operations I needed to add from the error messages, and then you have to increase this every time you add an operation. So the error messages on this were quite helpful, but if you don't want to use the micro op resolver, you can just use the all ops resolver instead. So I've left this in as a comment. which was also a comment from the example code. And then just run it as normal, as is on the other code. Just do the inference. And once I've done my inference, I find that the letter with the maximum confidence and the letter with the second maximum confidence. So the two most confident letters of what it could be. And so I iterate through all my outputs and I find the maximum and the second maximum. And then I write these two letters to the TFT screen, and I'll show you how that works in the demonstration, which I'll give next. So the last thing I wanted to say is that the pin connections for the TFT, I've placed those in the description for this video. And I'll see you in the next scene. I've uploaded the code to the ESP32, and the hand needs to be positioned fairly precisely in front of the camera, which is why I've done the extra work to include this TFT in the project, so I can see where the hand is, I can see what the camera's seeing. And so basically the user has 5 seconds to position their hands, and then the code makes the inference about what letter is being shown by their hand, and displays 2 letters with the highest confidence. So the top letter has the highest confidence and the second top letter has the second highest confidence. And I'm using the 2 top letters so that in cases where it's incorrect, I can see if it was at least close, and if I can tune it a little bit to get the correct result. Anyway, I'll do the demo now and I'll talk about the results in more detail after the demo. A. B. C. D. E. F. G. H. I. I. V. W. We saw that for most of the hand symbols, the correct letter was in the top 2 identified. And this is a good sign because it means that we can fine-tune the network. So there's a couple of points I'd like to make. Firstly, the training data that I used did not have any information about the camera environment. So the noise, the lighting, the background, a typical user, what my hand looks like, I guess my accent with the symbols. So what we can do is we can collect data from our actual environment and use that to update the TensorFlow network, so we can continuously train the network with data so the network adapts to the environment. And the other thing I want to mention is that the training data consists of 28 by 28 images, which are already segmented. So if you've got a picture of a person with their hand out, it's not going to pick that up because the hand part has already been segmented in the training data. So one thing you could do is we could expand to larger images and train it on that. So say 96 by 96, and we can probably find some of these on Kaggle. But increasing the size of the image will increase the size of the network, will increase the number of parameters. And this is mostly due to the fully connected layer that goes after the convolution layers, but before the output layer. So that fully connected layer that goes between the convolutional layers and the inference layer, the softmax layer, is going to have a lot of parameters in it, and the number of parameters in that is going to depend on the size of the image, the number of pixels in the image. It's going to scale with the number of pixels in the image. So now it would be interesting to see how big a model we can fit on the ESP32, because this model worked quite well and it was relatively quick. But from playing around with it, I actually think there is still a fair bit of room to move, especially if we're going to use PS RAM, because I didn't use the PS RAM for this project. And also, before I go, I just want to add that it should be fairly easy to implement any other TensorFlow computer vision models on the ESP32 without having to change the code that much. So you can basically just copy and paste your models on, and then change, I guess, the number of categories and stuff like that. So I've made the code available on GitHub. Thank you for watching, and I'll see you in the next video, hopefully.